Good evening, everyone, and welcome to this evening's lecture. Our guest speaker tonight is an associate lecturer and consultant at the Open University. He is a geologist and tutor in planetarian science and geology with a special interest in meteorites, island volcanics, and geochemistry. He also writes popular pieces for The Teacher magazine, and his research articles have been published in Britain, Poland, Portugal, and Canada. Michael also has an interest in furniture, clocks, and barometers, and is a keen conservationist. Would you please give a warm welcome to this evening's speaker, Michael Czajkowski? Okay. All yours, Michael. Thank you.
Quiet applause. Well, thank you for that. I've had one like that before. Well, good evening, everybody. Nice to see you all. I suppose now the point I should now share my screen. Okay, that should be slightly better, I hope.
Yes.
So Mercury the messenger. So basically, I'm going to talk about the planet Mercury. And so what we'll look at is a brief history of observing and initial assumptions. We then look at what Mariner 10 told us, then what Messenger is telling us, and of course we're still looking at the data we get back from Messenger. A little bit about interpretation, or some of the ideas associated with the interpretation, because as I'm sure you will realize that ideas chop and change, according to scientific debate and as new data comes along. So that gives me a chance to look at a bit about Mercury as a messenger for solar system dynamics, and then possibly what's going on in the future. So let's look at a brief history, pre-Mariner 10. Until really 2008, 2009, Mercury remained really very mysterious, most mysterious of the inner planets, because it's so close to the sun, makes it very difficult for earthbound observers. And historically, it was often thought to be two planets. The earliest observations were from Assyrian table from the 14th century BC. The Greeks called it Apollo when it's visible in the morning sky, and Hermes when it's visible in the evening sky. And this idea of two separate planets stayed around for a long time. The Maya represented Mercury as four owls, two for the morning, two for the evening, that served messengers to the underworld. And also here on the screen, there is a model, an Arabic model by Ibn al-Shatiras, showing Mercury and obviously using the multiplication of epicycles, which were popular with Ptolemaic times, to actually show how the very unusual rotation, rather the orbit of Mercury worked. The first telescopic observations of Mercury made by Galileo in the early 17th century, and he couldn't really see the phases of Mercury, and quite frankly, having seen his telescopes in the Galileo Museum in Florence, I'm surprised he could see anything, because the magnification really was so low. A reasonable sized pair of binoculars is far better magnification than what Galileo could see with a telescopes, and how he knows he managed to see the rings of Saturn really is rather beyond me. The first observation of a transit was made by Pierre Gassendi in 1631, and he used the information given by Johannes Kepler with his predictions of orbits very successfully. And then in 1639, Giovanni Zuppi used a telescope to discover that the planet had orbital phases similar to Venus and the Moon. And that demonstrated, of course, that Mercury was a single planet. In other words, there wasn't an evening and a morning planet. It had to be one planet, rather like Venus. It has rather a peculiar elliptical orbit, which precesses in a very short space of time. And in 1859, the French astronomer Urbain Le Verrier reported that the precession could not be completely explained by Newtonian mechanics and perturbations by known planets. He suggested there may be other bodies going around the sun which we can't see, and he termed these corpuscles. And so there might be other objects there that are giving these rather peculiar orbits that we see for Mercury. And the precession is measured to be about 5,600 seconds of arc per century. And in fact, if we take all Newton's equations and all the other information we have with from the planets, etc., and the fact that the Earth actually rotates around the Sun, there's an actual shortfall of 43 seconds of arc per century. And this really took a bit of explaining. And the other theory was produced by Einstein, who said that the orbit of Mercury could be should possess by an extra 43 seconds of arc per century, according to his general theory of relativity. He noted in 1915, however, in the process of completing general relativity, that his 1911 result was only half the correct value. He then calculated that the actual value was distorted as a result of the gravitational bending of light by the Sun. And of course, as you know, that was a very important scientific discovery and has been used for all kinds of things for studying astronomical bodies where you have light bending. So let's look at Mariner 10 and what we learned from that. Mission objectives was to measure Mercury's environment, atmosphere, surface and body characteristics, and also to make similar investigations of Venus. So I'm not going to bother with Venus because obviously we just don't have time. Mariner 10 photographed part of the sunlit hemisphere during each approach, passing behind the planet and continuing to image the sun-facing side as the aircraft receded. So basically the problem was it only actually managed to image about half the actual sunlight from that side. Obviously not the dark side, because it just happened to be, but by the time that the spacecraft came around, it was always in the wrong place, or rather Mercury is the wrong place, and we didn't actually see any of the rotation. And the body itself is quite small. It's smaller than Titan or Ganymede. The radius is 2,437.7 kilometers and has a very high density of 5.43 times 10 to the 3 kilograms. So it's quite a substantial density, and that suggests that the density is about 70% iron and about 30% silicate rock in very simple terms. So it has quite a large iron core. The eccentric orbit also relates to the actual planet's rotation. It rotates 1.5 times after two complete orbits. After one orbit. So after two complete orbits, the same hemisphere is again illuminated. And this is actually rather an odd characteristic. You would expect something that small and so close to the sun to be having the sun side facing the sun all the time. But oddly enough, Mercury still rotates, albeit very extremely slowly. And the estimated structure, certainly by 1990, was that there was a mantle and crust about 600 kilometers thick, and the core was about 1,800 kilometers radius, and the core represented about 42% of the volume, which is very high. To give a comparison, the Earth is only 18%. The density, however, is much lower than expected for an object that formed in the position of Mercury. If we think about the actual amount of material available for planetary formation in that part of the solar system, it should have been much higher. And one of the things used to explain why this may be the case, and particularly why there is a large core with a very thin mantle, is that Mercury was impacted by a large body very early in its history. The cores of the impactor and Mercury itself, or proto-Mercury itself, coalesced to form one core. It's rather the same when the moon formed around the Earth from an impact. The core of the impactor and the core of the Earth came together. And in the case of the Earth, of course, some of the mantle that sprayed off into space traveled around the Earth and coalesced to form the moon. However, Mercury is very close to the sun. And anything that's going to go up in the orbit of Mercury is more likely to be taken straight into the sun plus the fact, of course, Mercury itself has a very low gravity, so it's not going to be able to retain a lot of material, you know, to form a moon around it. And but of course, some of the actual material that went into space would have actually coalesced back onto the surface. But that, even today, is still considered the most general plausibility of how Mercury got its rather thin mantle. Model from a 35 kilometer per second impact. Several models have been made, they're all slightly different. It showed Mercury, like moon, was heavily cratered. And in this case, the craters are named after famous artists, musicians, writers, etc. This is the Czajkowski crater. Well, I had to mention this one, of course. The International Astronomical Union have a very weird spelling here, Czajkowski. In English, it will be Czajkowski here. Anybody who's anything about a musician will know that spelling. And in Polish, of course, it's my name, Czajkowski, and actually Krater Czajkowskiego is actually the Polish spelling for Czajkowski crater. You can see the outline here, rather aged and degraded, rather like me, I suppose. Certainly a very old crater and heavily pockmarked by more recent craters. One of the big objects seen was, of course, the Caloris Basin. Only a part of it was imaged. The rest of it was in darkness. Very massive basin, you can see here, formed by a giant impact very early on in its history. Has lots of these so-called wrinkle ridges. And these are either tectonic features caused by shrinkage of the lavas, or could be the edges of lava flows. And of course, those of you who observed the moon will have seen edges of lava flows in the bases of these very large craters on the moon. And we were able to draw up very clearly maps of the fractures and ridges associated with the Caloris Basin, which would have formed when the impactor actually struck. On the opposite side, we have what's known as the weird terrain here, which is very heavily cracked and faulted. Obviously, it's been overlaid by more recent craters, but this fractured and smashed terrain on the opposite side is quite an interesting observation and gives us some clues perhaps about what happened. We also have some interesting tectonics. These are compressional ridges here. This one is the Santa Maria Rupes. Rupes is just simply a scientific astronomical name for a ridge or scarp, like an escarpment. And you can see how it cuts through older craters and has been overlaid by younger craters. And as you'll see later on, these actually are quite important to understanding the history of Mercury. We can see here this section, how they're formed. This is Discovery Rupes schematic. And basically what happens is a situation we call reverse faulting, where in this case, material here to the right has been thrust over the material to the left and produces what we call crustal shortening. And we see this actually, I mean, you're sitting in Mansfield, I'm sure if you go to the Peak District, you'll see lots of evidence for this if you look. It's quite common in geology, especially where areas have been disturbed tectonically, like the Peak District. And what we think happened is that these were formed as the planet's core cooled very early in its history. The crust would have cooled first. The interior, of course, would have remained hotter for a long time afterwards. But as that cooled, then obviously the core shrunk. It would basically have dislocated the mantle, resulting in these thrust features. Have some very good maps from Mariner 10. This is the North Pole here. This gap here, of course, is simply lack of data in that area, showing some nice volcanic plains here, rather like that we see on Mars and the Moon, but with very limited craters, and a more heavily cratered southern hemisphere here. This is a composite image, mosaic image, showing here one side the Coriolis basin here, and this side here the weird terrain, and here's these rather smooth, you can just about make them out volcanic plains. Now obviously there's a big difference between the daylight side temperature and nighttime side temperature, so the weathering effects as a result of that expansion and contraction of the rocks must be quite dramatic in actual fact. Although because the surface is quite dry, it probably doesn't shatter the rocks in the way it would say in a desert here on Earth. We have very cold nights and very hot days. Nevertheless, there's a lot of information here, excuse me, to set up a geological time scale, which is very similar to the moon. We have down here a whole series of very large craters being formed, rather like we have on the moon. In the Imbrian period, here we call it the Tolstoyan period, and a series of very large craters, and the Calorius Basin was probably one of the last major basins to be produced at this time. We have pre-Tolstoyan craters which are smaller, like we also see on the moon, which are pre-Imbrian. And then, of course, afterwards, we see a gradual declining of craters. We have the lava plains here forming in the Calorian period, just after the late heavy bombardment. And that, again, is very similar to the lava flows that we see on Mars and the lava flows that we see on the moon. And then we have a period in really where numbers of craters and numbers of large craters sort of diminish with size. Sorry? Oh, I thought that was a question, sorry. If you look at the distribution of small volcanic plains on Mercury, we see they really occur all over the planet, not like where they're restricted to simply to one hemisphere. The pale grey are areas of cratering. The darker grey here are Calorian lava plains. Obviously, they're obscured by later cratering. And remnants of the older volcanic plains are here shown in black. Tolstoyan are shown here in black. So it's pretty well random all over the surface. But say it's not necessarily to the extent of the lava fields so much that these are areas that have been left, not obliterated by mass cratering. We hope to find out more, of course, with Columba. We also discovered, of course, a magnetic field. This was a great surprise. It wasn't known until 1974. And to have an actual active magnetic field on a very small planet like Mercury has really, changed our ideas about planetary formation. If you look at Venus, very slow rotation, doesn't have a magnetic field. Mercury, slightly quicker rotation, does have a magnetic field. Mars doesn't have a magnetic field. The whole thing seems to be solid on Mars, although there is a remnant magnetic field on Mars. But the Mercury field is actually active. It's only about 1% of Earth's magnetic field, but nevertheless, it is actually there, and it is very observable. So what did we learn from Mariner 10? Well, we learned that the planet was heavily cratered and covered with extensive lava flows. And of course, we imaged the major impact Calorius Basin with its matching weird terrain. And the general idea is that we think what happened was there was a large impactor which produced a crater, Calorius crater, sending up material all over the place. And the shock waves would have traveled right through the core, which, although not completely solid, it couldn't be completely solid, otherwise it wouldn't be generating a magnetic field today. It has to be partly molten even today to actually generate a magnetic field. So it would have been probably more molten in the past, but nevertheless, rigid enough, if you like, that it could carry the shock waves all the way through the core out to the other side, where it shattered open the mantle here, producing this weird terrain. And of course, the other thing was a stronger than expected magnetic field. Conclusions: well, Mercury must have been completely molten in its early history, has suffered major impacts, and the caloric basin, for example, must have almost shattered the planet during the late heavy bombardment period. Caloric impact suggests core was almost rigid, stronger than the crust. Lower overall mass and thin mantle may suggest massive impact, which resulted in loss of mantle, and a weak magnetic field that's still active. And the other thing we found out, of course, was this amazing thing, the exosphere. It's not an atmosphere. An atmosphere, in theory, has to come from within the planet in the form of gas, like the example, the gases we have on Earth. But here in Mercury's case, we have an exosphere of sodium particles. Very, very thin, of course, not any kind of density we can establish as an atmosphere. But what seems to happen is that these sodium particles drift across from the sun, and attracted by the weak gravity of Mercury onto the nighttime side, which is cold. And then when the Mercury rotates, so that nighttime side becomes the daytime side, obviously those sodium particles become energetic thanks to the sun's solar radiation, and they go off into space again. And that results in a kind of cometary tail behind the planet itself. And that again was something really quite new. Okay, so let's look at MESSENGER. Launched in 2004, the aim was to study Mercury's chemical composition, geology, and magnetic field. It made 3 braking flybys between 2008 and 9 and went into orbit in 2011. During its stay, instruments revealed details of Mercury's magnetic field and suspected water ice at the North Pole. This is a diagram of its flight path. And the thing about Mercury is it's close to the sun. And that means that you've got to slow the spacecraft down, otherwise it will go straight into the sun. We're used to the idea of using slingshot technology to actually send spacecraft into faster orbits further out into space. In this case, we have to do the opposite. We've got to use these braking maneuvers to actually slow the thing down. And as you can see from the bottom here, there are 5 of these major braking maneuvers. The first time round, where did we start from? Where's Earth gone? There we are, Earth somewhere. There we are, launch. Okay, so initially came round here and close to Mercury the first time, came round again, inwards to the first flyby past the Earth, and then subsequent flybys past Mercury in an attempt to slow it down sufficiently that it would go into orbit around Mercury. The trouble also with Mercury, of course, it's a very small body. And to get into orbit around it, it's very difficult. You've got to slow it down enough that you could, the gravitational attraction of Mercury is sufficient to keep it in orbit. MESSENGER, of course, didn't go into an orbit round Mercury. It did flybys going around the whole system, Mercury system, going right around the other side of the sun. And that was the problem. It meant it encountered the same surface each time it went round. This is an example of the first braking flyby past Mercury. Earth is over here. So there was 5 minutes when it was impossible to see what was happening with the spacecraft until it came, where it disappeared behind the planet, came out the other side, and continued on its course. Now, MESSENGER carried far more instruments than Mariner 10. Mariner 10 had only a very basic instrument package. MESSENGER carried 11 instruments including wide and narrow angle CCD cameras, gamma ray spectrometer, neutron spectrometer, X-ray spectrometer, which are all those spectrometers very useful for measuring the composition, therefore determining the geology of the surface. Magnetometer, of course, looking at the magnetic field. Laser altimeter for determining height and therefore producing proper height determining maps. Atmospheric and surface composition spectrometer to determine the exosphere that we see around the planet, even though it's very thin. Energetic particle and plasma spectrometry, measuring charged particles in the magnetosphere using the energetic particle spectrometer, and also looking at the charged particles coming up from the surface using fast imaging plasma spectrometer. These charged particles on the surface are produced by cosmic radiation hitting the surface and releasing things like gamma rays. And we can look at those gamma rays and the speed of the energy of those gamma rays to determine what the composition is. And also there was radio science. Basically, as the spacecraft goes around the planet, any slight changes in the density of the planet will affect the gravity of the planet, and that means that the spacecraft is either pulled towards the planet or pushed away from it accordingly, and that means that we can observe from that basically changes in the density locally. Excuse me. This is digital elevation model. The red areas are high ground and the blue areas and purple areas are low ground. These are the northern plains here, which are low lying. Coriolis Basin. This is the equator going here. It's rather an odd map. We've got the equator going around here in the middle, and this outer edge is all the southern pole. So it also, or near to the southern pole, it all kind of joins up. So you're looking at a rather an map here, and it's really here to show the northern plains, which is the area of interest, of course, for looking at whether any Mercury existed, so any water existed on the surface of Mercury, in some of these very deep craters. So the first thing was to identify areas on Mercury that are always going to be in shadow. And if they're in shadow, of course, they're going to be at very low temperatures, something like 10 Kelvin. Where there's no atmosphere, the sun side is going to be something like 700 Kelvin. Immediately you get into a shadow, it drops down to 10 because you've got no atmosphere to produce any kind of heat transfer. So these are potential areas to look for water. And in actual fact, this is some examples where we found water here, near the North Pole. And so we were able to confirm by hydrogen atoms being given off that in fact water existed in a lot of these craters near the North Pole. The water itself probably arrived by comets or maybe a few asteroids, which have, depending on their composition. It's worth noting that comets didn't really deliver water to the Earth. The chemical composition of most comets is just wrong for water on Earth, but it probably would contribute to a very minor point. Most of the water on Earth actually came out of the interior of the Earth. That's just from the side. If we look at the extent of Mercury's northern volcanic province, we can see that the largest one is really quite large. It covers most of the United States. And as I mentioned before, probably formed about 3.5 billion years ago, and thought to be about 1.5 kilometers thick, filling in deep craters, and altogether they cover about 6% of the surface. So it's quite a large area. And like Mars, these tend to occupy very low-lying areas. And we get an idea really about the thickness by looking actually at ghost craters like this. Look on the right, we can see a large ring basin, which has been flooded by lavas entering from the side here and flooding most of the features of the crater of the interior, including part of the actual ring peaks here. And if you look here on the left, we see what we call, or Americans love to call, pie crust structure. And basically that means that as the lava flowed over these craters here, drowning them, it must have been thin enough that when the actual lava itself solidified, it then shrank, and then produces these ghost outlines of craters beneath it. If the lava is too thick, you wouldn't see this. So that suggests that the lava must be quite thin, possibly no more than about a kilometer and a half. Now, combination of instruments meant false colored images are possible. These aren't actual colors. We use this kind of false colors to give us indications of different chemistry, different surface chemistry, and therefore different chemical compositions of parts of the surface. This, for example, here is the Tolstoy crater itself, one of the very old craters. And you can see it's rather dark blue color in this image. We can see that the infill is of this paler grayish color, which appears to be mainly volcanic lava flows in each case. This would be impact lava in this one, but here would be external lava flows. On the other hand, we still have a rim here of the Tolstoy crater made up of the original material forming the which is formed underneath these lava flows. This is obviously a more recent crater here, but one deep enough that it actually penetrated the lava flows, bringing up this blue stuff, which you'll see the same color here, from depths. So we can use craters very nicely to actually give an indication of what's going on beneath the surface. This one here, Kaladasia crater, is probably more recent, is probably between the two in age, but also didn't penetrate here the lava flow. So we can put all this information together to actually give indications about the thickness of lava flows, because we know from the size of the crater what kind of depth it would be, basically. We can work it out. This is Calvino crater here. And that's impacted into a lava plain here, Radaki lava plain, which is rather shown here as orange, whereas the older outside surface is shown here as blue. You can see that the crater here has an orange rim, obviously of this lava material formed by the impact, but there's a little bit of the blue stuff from beneath is beginning to show through. And again, here we have other things like very similar things like this. We have some little craters here with yellow on the outside. And again, there must be different material excavated from depth. And in this case, we have a lava walls of deep blue, which again must be material from deeper down. So we can look at this and we can try and get an idea really of the kind of layering that's going on inside Mercury itself. And for example, Tectonic crater here, we have a floor of lava, impact lava here, infilling this crater. And also, again, small craters here, which we'll look at more in detail, actually, of material being excavated from underneath. But obviously, different color must mean that they're a different composition. We may not be able to tell exactly what the composition of each is, but we can make some guesses based on geological processes of what's going on. And clearly, the dark blue, for example, is very much older than the material here. And it does show, say there, that Mercury does have a layered structure. It's not just simply rock. We also have a greater resolution of the scarps, the rupees. This is discovery rupees. And you can see how it's shattered through this crater here. And very good image here of these tectonic faults. The sun is coming from the left to right here, of course, and you've got scarps about 2 kilometers, 3 kilometers high. And this again is a diagram showing how these thrust faults work to push this material up over. And we call this really crustal shortening. And by using the craters, the age of the craters and the way the craters have been offset, we can work out how far these thrusts have happened, how far the rocks have moved. and also the relevant age. This is Beagle Rupees, 600 kilometers long. As you can see how clearly it's distorted this crater here by offset, which was formerly flooded by smooth lava that was solidified. And the surface itself here has moved quite considerably. They're quite long and extensive. When we map all these, we find there is a very interesting pattern. One thing, they cover most of the surface. The other thing is that on the equatorial areas, they're more or less transgengent to the equator itself. So in other words, they're running across the equator. If we go to high latitudes, we see they're actually running horizontal. So that's interesting, and that needs explaining. And certainly it suggests that there's more crustal shortening going on around the equator than there is around the poles. Simply because there's more of this going on here. So you have a lot of crustal shortening around the equator. We were also, I'll come back to that in a few minutes, also able to image the Colorus Basin in bigger detail. This is the false come image. We see here the lava infill of this massive basin. We have craters that penetrate through the rocks beneath, showing this blue color. Remember, Mariner 10 only showed about half this basin, so we've learned a lot more about it with Messenger. And one thing we learned was that the room is actually bigger than we thought. Now at the center, you have what we call the spider. This is a close-up of the spider here with radiating grabens from the center. We're not quite sure really how this formed, but it probably relates to the cooling of the lava flows and possibly also the sinking of lava, maybe as the floor of Colorus Basin actually worked its way downwards. Crater formation, although crater formation is very rapid, in a matter of minutes, even with a big crater like this, the underneath is still very hot. So if that has molten any rocks at depth, or particularly if it's molten any part of the core at depth, and that then cools, obviously it will crack, that will contract, and then force in this radial graben pattern probably as a result. I mean, that's a bit of a speculation, but you know, it's as good a theory as anything else. You also find different kinds of volcanoes. This is actually a basaltic shield volcano, the kind of thing we see on Hawaii, or in many places in Iceland, or at the moment in the Canary Islands. You know, this kind of eruption is going on. And the thing to remember is that, without going too scientific about it, the different volcanic rock compositions will give you different volcanic shapes. So turning it around on its head, we can look at the shape of the volcano to actually tell us the kind of lava that's involved. And with shield volcanoes, it is very much basalt lava. So we have a crater here, with a series of vents. This is the edge of the deposits, and there's a partly filled crater which probably formed earlier on, and subsequent volcanic eruptions have partly infilled it. Around the edge of the Colorus Basin, we also found a whole series of very small volcanic vents. This is actually the southern edge, as you can see here. This is a close-up on the main map. And this is a spider up here, which we looked at earlier. And so clearly these vents are related to rim structures. Something to do, obviously must be do with the formation of the Colorus Basin itself. And particularly since these are pyroclastic deposits, and that's unusual. Very unusual indeed. And they're shown up here by their rather reddish color. And this one actually is shown up by its yellowish color. The volcanic cannot crater because you don't have the same kind of rims that we actually see with craters. Obviously, this is clearly a cratering rim here, where the rim is elevated. Here, we actually have a kind of basically a mound, basically with a hole in the middle. And this is a volcanic vent. And these are pyroclastic. And pyroclastics are basically gas eruptions. And that was something that you should not expect on Mercury. Now we have two types really of lava. Obviously are the raised intermediate type, the two ends of the scale. We have the effusive lava like this, which forms your shield volcanoes, and the same kind of lava that's going off at the moment in the Canary Islands and also on Iceland. And we have explosive volcanoes, like the kind like Mount St. Helens and other explosive volcanoes. And they don't form runny lavas, they're actually full of gas. And what happens then when it leaves the vent, it blasts the lava to fragments and comes back down as ash. And just to explain how this works, this is a diagram. If you imagine have a large magma chamber under a volcano, if there's a lot of convection going on in this magma chamber, it'll keep stirring the mixture all the time. And therefore, iron, magnesium, sodium, potassium, and all the rest of it, silicon, is there in the kind of amounts that it would be when that magma chamber formed. If that erupts to the surface, we then can get this shield volcano with very runny lava flows. If, however, for some reason, the convection stops, then early formed minerals, the early formed minerals, things like olivines and pyroxenes, things like that, which are very rich in iron, they will tend to sink out to the bottom of the magma chamber. We call it, in fact, cumulites. And that means the remaining magma is going to be enriched in gas and things like silicon, sodium, and potassium. And if that erupts to the surface, that has a very different composition. And because it's very gas rich, that's when you get these kind of explosions that you see at Mount St. Helens. And the result of that is you have a very steep-sided volcano, like Mount Fuji in Japan, for example. So basically, from the same type of basic rock in the mantle, you can actually get two types of lava. In fact, you can get more, but that shows you the actual extremes. Lavas here, if they do form, tend to be rhyolite dacite, and here they tend to be basalt. So returning to the Caloris plains, this is one of these vents, the pyroclastic vents. And we also see things called rimless pits, which are thought to be gas escapes. And they're all associated with the Caloris rim here. This is a close-up here. We have a pyroclastic vent with its surrounding deposits, like Mount St. Helens. And then we have a very rough surface here, which we seem to be hollows and pits, which we think are related to these gas escapes from gas within the lava itself. Now, why should it be that we see these pyroclastic vents around the edge of the Caloris basin? Well, simply because they're a feature of late-stage volcanism. And if you go to any kind of volcanic island where it's where the volcanicity has ceased, you tend to look at the rocks, and the early rocks are very much like basalt, things like that. And eventually, as volcanism wanes, you end up with pyroclastics. And so what's probably happened is you've got these pyroclastic vents around the edge of the Caloris basin, simply because you have a line of weakness there, which allows these vents to come through the surface and, of course, erupt with the ash deposits, gas and ash deposits. There's some more examples of these gas and volatile escapes. A lot of them are also associated with these rupees, these escarpments. And that again might be due to the fact that the rifting here, forming these rupees, put pressure on the underlying crust, and that allows, again, cracked up the surface, allowing gas to escape and bringing ash with it. So let's look closely at the volatiles. This is where it gets really very interesting. If we look, what we tend to do as geologists is to look at different minerals in relation to each other, ratios of one mineral to another mineral, which have different properties. Now, for example, potassium is a volatile element. Thorium is a refractory element. That means that thorium has a much higher melting point than potassium. And for example, if you think about the moon, when the moon formed, the material that went off to form the moon had lost obviously a lot of its iron and magnesium because that was left into the core of the Earth. But a lot of the volatiles would have escaped because they were of the very high temperatures of the moon formation. And so the moon is very rich with refractory minerals as a result. And we can see this on this graph here, where for each step we go up, there's a lot more thorium than there is potassium. So this is very indicative of the moon, which is very refractory in its composition. If you look at Earth and Mars, they are on a very similar line going here. And this line is much steeper. So we have a much higher volatile content in respect to refractory content. That's okay, that's fine, because we have pyroclastics on Earth. And there probably were pyroclastics on Mars at one time as well, although Mars is less processed as a planetary body. But then if you look at the Mercury, it's even steeper still. It's extremely rich in volatiles. And that is odd. It shouldn't be. After all, Mercury formed close to the sun. It should have driven off all the volatiles. Another thing we find, which is rather interesting, is looking at the sulfur in the regolith. If we look at older terrains, we see that the ratio of sulfur to silicon is very high. If we look at more younger terrains, we see that aluminium to silicon is higher. So we have a difference between the two. And that suggests that we have a crust, a mantle, which has changed over geological time. We started off with high ratios of magnesium to silicon, sulfur to silicon, and calcium to silicon, and newer terrains have higher ratios of aluminium to silicon. So what's going on in the interior, the sources from which magma is being generated is changing its composition. That is interesting because that is not happening, for example, on Mars. And it doesn't seem to happen on Venus, as far as we can tell, not to the same extent. So it's a bit of a mystery why it should happen on Mercury, which has actually a very thin mantle. So we have these rather interesting differences in chemistry. Now, magnetic field, of course, the messenger managed to reinforce our theories about the inactive field. We found that the axis of the magnetic field rotation was within 5% of the rotational axis. So not too different really from what we have here on the Earth. Local magnetic fields also exist, actually, which are produced on the surface by solar wind, but they are very, very minor in comparison. Solar wind plasma, for example, can interact within 500 kilometers of the surface, which is quite a distance if you think about it. The fluid outer core was detected as fact by forced annual vibration, in other words, looking at the wobble of Mercury. And one interesting thing was that the magnetic field is offset to the north. So in other words, although it's actually occurring on the same axis, it's displaced from the center to 20% further up towards the North Pole. And it's 3.5 times stronger in the north than it is in the south. So we can revise really what we see from Mercury as a result of messenger. One thing, we have a crust which is 100 to 300 kilometers thick and may well be layered. We have a mantle 600 kilometers thick, which may also be layered. And we have a core which is about 1800 kilometer radius. So the mantle and crust are previously thicker than is thought, although there's still some dispute about that. The offset magnetic field is interesting because it means that there's more protection against high energy electrons in the north part of Mercury than there is in the southern part of Mercury. And that greatly affects the amount of surface weathering goes on. There's more surface weathering going on in the south because it's less well protected. Like the moon after formation and late heavy bombardment, there was widespread volcanism, infilling low-lying depressions. Major impacts, Caloris Basin, weakened crust in the mantle, and in changing internal structures, so the mantle evolved differentiated like on Earth. That's certainly, and that's not happened on the moon. We don't really know about Mars, to be honest, because we just don't have that kind of information. But if it is, it's actually quite a thick crust there. And also found out the surface is rich in sulfur. So the mantle and crust is thicker than formerly thought. Later volcanism, most recently associated with pyroclastic volcanic volatile rich deposits, which is actually a characteristic of waning volcanism. We see this on Earth. I used to go to Madeira a lot with my students, and I can show you good examples of how this waning pyroclastic activity came into being. The Rupees thrust zones produce large-scale contraction, especially in low latitudes, associated with cooling and rotational loss. So if you think about Mercury to start with spinning, obviously it's going to be like a squashed orange. The Earth today is like a squashed orange. If you go to the North Pole, you are closer to the center of the Earth than if you go to the equator. And that also means, for example, if you want to lose weight, go to the equator because you'll weigh less. So obviously, what seems to have happened here, originally Mercury was spinning quite well and has since slowed down. And obviously that's pretty not spinning, but it is spinning, but just extremely slowly. And as a result of these contraction cracks have appeared with crustal shortening as a result. And the unusual rich nature of volatiles was totally unexpected. And Mercury should have a low volatile index. In other words, it should be rather like the Earth's moon because it formed close to the sun. And therefore, we'd expect all the volatiles to be driven off during the formation of Mercury, especially also after that major impact. And for our general models of the solar system formation, for example, which formed from a giant molecular cloud, we know that the center got hotter and hotter and hotter to the point that everything was vaporized to a diameter of just beyond that of the Earth. And then when gradual cooling took place, refractory minerals started to condense out to form the rocky planets. This is a log scale here, showing the amount of material available for planetary formation. And we can see from this, for example, that there's a lot of material, especially for Mercury and Venus, less so for Mars, possibly. And once we get to the snow line, at the point where volatiles could condense as ices, then of course we start to see giant planets which have less rocky material, but could scavenge ice particularly, and gas, which was not vaporized by the sun because basically it was far enough away not to be affected by the sun to that great extent. That's one reason why these do have a very ice and gas covering to the planets and also to their satellites, whereas here in the inner solar system, we don't. This line here actually represents a snow line or ice line, depending on your point of view. The high sulfur content may be due to the high element density. It can be modeled to condense at high temperatures depending on the presence of hydrogen. So if there's plenty of hydrogen around, if the inner solar system was under very high reducing conditions, this may explain the very high sulfur levels in the Mercury area of formation. I mean, here's the same kind of thing, of course, with Io, which formed obviously in the accretion disk of Jupiter, also has very high levels of sulfur. And again, if Jupiter could hang on to a lot of its hydrogen for long enough to produce a very reducing environment, that may have also allowed sulfur to condense out on Io exactly the same way. Now, the potassium problem is a volatile, as I said, should be absent. Mercury has a lower density than expected, and there is evidence of large impacts that should drive off volatiles. So basically, potassium and similar elements should not be there. So what might have happened is, and this is not agreed 100% by everybody any means, that Mercury may have formed on the other side of Mars or even close to Mars, and then migrated in. And if it had migrated in, that would put Mercury into a very eccentric orbit. And this 3-to-1 spin orbit resonance may reflect the former chaotic orbit involved with Mercury spiraling in towards the sun. This also would have resulted in high levels of surface volcanism, particularly when deaccelerating around the sun. And of course, reduction of spin and cooling led to volatile loss and later pyroclastic eruptions. So what of the future? Well, we have Bepi-Colombo, launched 2018 on a 7-year mission, 2 spacecrafts, a planetary orbiter and a magnetosphere orbiter. And some of you may have seen here the first picture sent back by Bepi-Colombo on the 1st of October. So that, ladies and gentlemen, is the end of my talk. Thank you for listening. I shall now stop sharing, and of course, if you have any questions, I'll be very happy to try and answer them.